hope you can hear me clear and everyone stay safe. So today we will go into the next chapter, the chapter 6, which we will talk about the isoparametric formulations. So if you have any questions, feel free to type in the chat box, right? And for this week onwards, I will provide the attendance link to you. You don't have to type in your name in the chat box, all right? So let's see. Okay, I think the screen not showing yet. All right, so wait for a while for me to double check. Okay, sorry for this delay. I will check again. Okay, so I hope you can see it now. All right. So on the isoparametric formulations, we will again derive the stiffness matrix and so on. Okay, but this is a different way of formulations. Okay, so before we start with the content, I just want to make sure that everyone have logged into the Google Classroom. Okay, there are tests and quiz there, all right? And also from the recording itself, also after the recording, I will put the timestamp in the YouTube video in the video description. So what you can do when you want to do the revision, you just go through the description and click on the timestamp that's on the part that you intend to listen to, right? So at the end of these sessions, there will be a short quiz related to this topic, and that will be the last quiz for this course, right? So what is the isoparametric formulations and why we need it? Okay, so as we can see that the development of the element matrix and equation expressed in terms of the global coordinate system is quite easy, but then when it become large, okay, for a more complex element, it become difficult. Okay, therefore this isoparametric formulations was developed to actually solve this problem when we deal with a more complex type of elements. Okay, so the isoparametric methods may appear tedious, okay, at the beginning, okay, very confusing, but then it is easier to program, right? So it's a simple computer program formulations, and it's generally applicable to two-dimensional, and we can extend it to a three-dimensional type of problem. The isoparametric formulations allows the elements to be created, and that is where the elements may be not rectangular in shapes, or also it has a curved type of shape, right? So the isoparametric formulations of the, for this case we will only or for this course we will only deal with the plane type of elements, all right, from the simplest one-dimensional or maybe a bar elements. Okay, then we move into the two-dimensional type of elements, the plane type elements. So here the formulations, as we can see, the terms isoparametric is come from the words iso, which is the same, okay, and then it's have the same parameter, so it's parametric. So it's related to the use of the same shape function, okay, the interpolation functions that we have discussed, and I have stressed it from the beginning of the lecture, all right, from the beginning of the chapters of this this course. Okay, so we will see that from a prismatic type of prismatic bar type elements, then we move on into a plane type like CST and Q4. We also try first to derive the shape function. So this shape functions itself, when we apply it using the same shape functions, okay, for the same type of elements, we will call that as a isoparametric formulations. Okay, so what is the idea behind that is that, as we see from the previous maybe Q4, okay, Q4 type of elements, so the one of the shape functions we have this form. Okay, so indirectly it is a constant which is BH, okay, then minus BY XH and then XY, right? So we have a kind of function, shape functions which have a constant plus constant X plus constant Y plus constant XY, okay, sort of, right? So I will use XY here, okay, just for these cases, okay, just to illustrate that previously we depend mainly on the global coordinate, the X and Y coordinate, right? Whereas in this isoparametric formulation itself, now we try to incorporate I would say a natural type of coordinate, all right, which we would use as maybe S and T, all right. So here we will use the S and T to describe the similar shape functions, okay. So if you look, comparing these two functions, they are exactly the same, okay, only the parameter is the different, right? So we have A1, A2, A3 and A4, but it's actually is the same, right? So in the parametric elements equation itself, we will use a natural kind of coordinate system instead of a coordinate, the Cartesian coordinate maybe, or a cylindrical coordinate that we use to, okay, to describe our elements. This isoparametric elements itself is similar, only the coordinate system now we are using, instead of XY we will use S and T, right? So this natural coordinate system S itself is attached to the bar itself, okay, if it is a prismatic bar, okay, and it will be remain along the axial length of the bar, okay, regardless how the bar is oriented in the space, okay. So in that particular sense itself, then we will see that when we attach this kind of natural coordinate system, then it is much more easier to describe or to obtain the shape functions based on this natural coordinate system, instead of identifying the exact global coordinate system, which is the XY, right? So in order to, at the end, after we do the computations, we have to match it back to the natural coordinate system or the global coordinate system at the X Y axis. Then we will use what we call a transformation mapping, okay, to map them back, okay. So we will look into again the isoparametric elements formulations, we will start with the bar elements. Okay, we start with the bar elements. So this is a bar element. Okay, so previously when we start to derive previously for the bar elements, we will use not 1 and not 2, right? So this not 1 and not 2 itself, we will not put a notations with, or we mark them with a coordinate. Okay, so the coordinate may be x1 and x2, right? So this coordinate can be any numbers, like maybe this is 1.2, this is maybe 3.4. okay, so when this element itself change positions, this coordinate will change accordingly, right? But then when we use a natural type of coordinate, the x-axis itself, then we do not stick to the global coordinate now. All right, instead we will just put at the midpoint, we will denote as the s equals to 0, then at the end we will put s equals to 1, and on the other end we put s equals to -1, right? So it is become like a localized coordinate system for that particular element itself. Okay, so it will be much easier if we do it in that way, okay, before we do a mapping back to the original global coordinate, right? So as we can see that this s-axis not necessarily need to be parallel with this x-axis itself. Okay, it may or may not be parallel to the x-axis. Okay, for this case, for this bar element itself, it may not that clear. Okay, because we still align our x-axis and the y-axis, or maybe in the bar itself we will align the x-axis along the directions of the bar. Okay, so it may not be obvious, but later on we will see another Q4 examples where this x-axis not necessarily have to be parallel with the x-axis. Okay, the s-axis not necessarily parallel to the x-axis. Okay, so first we will consider two nodes. Okay, then each node will be subjected to a displacement. In the bar itself, we will only consider the axial displacement, the u1 and u2, right? So if you still recall back, the displacement for a bar element only along the bar directions, okay, or the bar length itself. Okay, so what we can do is we form the relationship between the global coordinates and the natural coordinate itself. Okay, so let's say here we have a special case when the x and the s-axis are parallel. Okay, for this bar element, assuming they are parallel, okay, to ease our formulations. Okay, therefore we can relate these two coordinates itself using these equations. Okay, where we have to identify the centroid of the element. Okay, from the centroid itself, it will be half length of the bar element, give us the first node, and the other half length of the element itself. Okay, this is the centroid. We will get the other point, okay, or another node itself. Okay, so this is only a half length, right? So L/2. Okay, so this is how we can relate them, all right, directly. Okay, so if we further derive for the mapping of the coordinate itself, okay, we can always put in the x1 and x2. Originally there is x1 and x2, okay, divide by 2. Okay, we put into our centroid coordinate, right? Once we put in, we rearrange, we will get the s in this in these formulations. Okay, so from here again we can always relate back. Okay, we can rearrange and to form this form. Okay, this form. Okay, so this form, as we can see, is very similar to this. Okay, we have a constant and another constant which is related to the s, right? So if we can relate in this kind of form, then it's easier for us to always map them back to the global coordinate system, right? So solving those parameters, okay, from the previous equations, from this equation itself, okay, now we will try to solve them, okay, bring them out, okay, to group them, so we will see that particular form, right? So if we express them in the matrix form, then we will have n1, n2, x1, x2. Okay, so we have x1, x2, so this is our n1, this, and then this is our n2, right? So eventually we will get these shape functions. All right, so these shape functions is derived based on the natural coordinate, the s itself, right? So you don't see the x coordinate over here, right? So here we can easily remap back. Okay, if we want, we just put back our relationship, okay, to this equation. We will get the shape function in terms of x. Okay, but if you recall clearly, again, this shape function itself is exactly the same format, the same form with the bar elements, okay, which we have derived previously for the global coordinates. Okay, that's why we would say that this is a so-called isoparametric element. Okay, so the idea is still the same. For a shape function itself, the summations of all the shape functions value should be equals to 1, right? So if this is a bar at coordinate -1, n1 should be 1 and n2 should be 0, add them up equals to 1, right? And so on. So eventually the summations of the shape functions remain equals to 1, okay, regardless you are using the isoparametric formulations or the previous shape function formulations derived in terms of global coordinate system. Okay, so we can always resubstitute all the value in, right, to obtain the coordinate for each of the node. Okay, so now our main focus is to use the natural shape functions, natural coordinate, right? So we will now again use the displacement functions. Okay, after we have the shape function for an element, we will start to derive for the displacement function and so on. Okay, so if you notice that the displacement functions is just regroup of the previous. Okay, so when we regroup them, we have n1, n2, the previous x displacement and displacement number 2. So this n1 and n2 is again same with our previous formulations. Okay, the same n1 and n2 for the isoparametric. Okay, so when we notice that they are the same shape functions, okay, at the same nodes, regardless it is about u or about x, okay, then we say that element is isoparametric. All right, so the idea here is that to use a natural coordinate system to replace the global coordinate system for each of the node to determine the displacement, right? So because of that, there is displacement functions expressed as a functions of the natural coordinate system. Therefore we have to again relate them back to the global coordinate system which is related with the x, right? Okay, the displacement, the changes in the physical form. Therefore, we must apply this chain rules to differentiate the functions of u. All right, so we will differentiate du over ds. Okay, so we have the chain functions. Okay, instead of x, okay, we have to use s, right, the natural coordinate. So using that, when we differentiate them, okay, we will obtain these formulations. Okay, and also we know that du over dx is actually the strain, okay, in the x directions. Therefore, we can from here put in whatever equations that we have derived previously, okay, into our strain. Okay, so when we put it in, then we group, it will form in this matrix form. Okay, and we could say that this strain, okay, can be related to the displacement by this strain displacement matrix. Right, so this strain displacement matrix is given by 1 over L and 1 over L. Okay, and also once we get the displacement, as before, we need to find out the displacement before we can get the stress. Okay, so once we get the displacement, we can use the Hooke law, apply this into our equations. Okay, multiply by the Young modulus, we will get the stress, right? So eventually we have these formulations. All right, so what happened is that we will notice that for a simple bar elements, okay, there is no real advantage. Okay, it's not clear because, as you can see previously, to obtain the strength relationship, we have to do a chain rules differentiations and so on. Okay, there is no actual benefit. Okay, but then if we go into a higher order elements, okay, when we can easily attach the, or we can easily represent the coordinate of every single node by using the natural coordinate, by putting 1, -1 and so on, that will be much easier, okay, for a higher order elements. Okay, and that will also helps us in formulate the computer program easier. Okay, instead of always grabbing the coordinate from our simulated model, okay, in the software, okay, it will always assign the point, okay, and then after they compute, and at the end only they match it back to the coordinate. All right, or map it back to the coordinate itself, right? So after we get those things, we can always construct the element stiffness matrix now, okay, by using the stiffness matrix formulations, which is an integral of the transpose B, D, B, A, and dx, right? And also we can transform the coordinate, the x coordinate, into the s coordinate, okay, by using these prescribed formulations, okay, which involve a Jacobian, right? So this is a determinant of Jacobian, right? And for a single dimensional case, okay, this determinant of Jacobian is simply the Jacobian itself. Okay, so we just calculate, okay, and we will obtain the determinant of the Jacobian for a single bar is actually L over 2. Okay, so we just apply back. Okay, so this is the idea behind the derivations itself. Okay, so now since we already obtained the Jacobian, okay, we just apply it back to our previous equation. So remember, we have this S domain, right? Our coordinate, or the node itself, is expressed in terms of the natural coordinate. So if we need to obtain the stiffness matrix, therefore this part have to be inserted here, right? That's why we have to include these Jacobians. Therefore, now that equation, since we know for a single dimensional element itself, the Jacobian is L over 2, we just have to integrate them using these equations. Okay, now it become ds instead of dx, right? So we integrate accordingly. Okay, this is the finite integrations. Okay, so you just integrate, and eventually we will get this stiffness matrix, right? So this stiffness matrix is exactly the same stiffness matrix that we obtained in chapter 3, right? So we can see that the isoparametric formulations give us the same results, okay, which confirm that this formulation is proper. Okay, only the advantages here is that when we apply for a computer, then it will be easier to express the knots with the natural coordinate system, okay, instead of the global coordinate systems. Okay, so you also notice that I already highlight here the AE with the red color here. Okay, what it means is that if you still recall, okay, all this formulation itself, those value, okay, for an element, we can construct it from the model itself, okay, from the dimensions of our model. Okay, so the L itself, we can tell, okay, the software can tell how long is the if the element itself, okay, the L itself. Okay, but then what we need to insert as a user, okay, is the area. Okay, in order to for the program to run, okay, using the prismatic bar elements, we have to insert the area, cross-sectional area of the bar itself. Okay, also we have to insert the Young modulus for the material itself. Okay, so this two parameter must be properly referenced, okay, or maybe properly checked, okay, when we put it in our software. Okay, because in the software itself, when we select how do I say, when we select a bar element, okay, when we select a bar element, we can run, okay, without defining what is the area and E, because by default, without defining, the software may put 1 or 0, okay, they will still give you a result. Okay, but this is important, that you must aware that when we apply this kind of finite element, okay, the element that we select, then we have to provide this detail, okay, the A and the E to the software, okay, in order for them to calculate proper results. Okay, so now for others formulations, the object or the model will be subjected to other boundary conditions, such as they are subjected to the weight, okay, the body force itself, and other things. Okay, so how we can deal with that? Okay, we will form this so-called body force matrix, okay, to identify the natural coordinate system of S. All right, in terms of S itself. So how we do it? We just integrate, okay, 3 times, okay, respect to the volume. Okay, so we have to integrate over the whole volume itself. Okay, but then for a single bar element, okay, we will see that for a body force, okay, we have to imagine that there is an area, okay, for our bar. Okay, that is the A, right? Then there is a length, okay, the L, right? So the A and the L have to be given. Okay, then this XB is what we tell the software to input. Okay, so the XB would be the body force per unit volume. Okay, so usually we will tell the software what is the force per unit volume acting on that particular body. Okay, so in this case, it could be due to the mass, okay, which related to the density, right? Is in terms of volume. Okay, So this parameter is depends on those things, okay? Then divide by 2. So we will interpret this body force as we have the ALXB representing the total body force acting on the element, okay? Since the A multiplied by L is the volume, okay, the whole volume of the bar itself, okay, and multiply by the our defined body force per unit volume, right? Then also in finite elements, okay, we would always define knots, right? Okay, so if we see from this illustration at the top, okay, we will have this geometry, original geometry, okay, which internally there is one small cube that we can extract, right? So this cube itself subjected to a body force, okay, that would be the weight maybe, all right? So the weight itself is acting on that whole cube. So how we could represent that, as we have learned it previously, this force have to be distributed and applied to all the knots of the elements, okay? So in a simple case itself, it will be acting on this knot. Therefore, we will say that the body force is equally distributed to the two knots, okay? It will be distributed over here and the others. That's why we divide by 2 with a weightage of 1, 1, okay? Equally distributed between them, all right? Same thing for a body, for similar to body force, we have the same formulation, similar formulations for the surface force, okay? Surface force is referred to the force that act only on the surface, not internally, right? So the surface force itself, again, we can see from the geometry, we can extract the cube out, okay? And this cube is actually subjected to maybe a pressure from outside, okay? So this pressure will be acting on this surface on the element, but then when we compute it, okay, it will transform this force, this pressure, into the force acting on every single node. But because it is on the surface, it will only act on the surface, okay, of this particular element, okay, not on the other surface, all right? Therefore, the formulation is very similar, okay? We have the L over 2 distributed, all right, between the two nodes itself, okay, with this ratio Tx, which refer to the unit force per unit length, okay? How much force acting per one length of that particular element itself, okay? So this Txl is the total force, okay, and it is uniform surface traction acting and distributed between the two nodes of the elements, right? So don't worry on these two parts, okay? It will just give you the idea on how the software, okay, that's most of the software, they use isoparametric formulations, okay? Therefore, what the software actually did behind that, okay, the idea behind those formulations, right? So again, we will look at another type of elements where we can apply the isoparametric formulations, okay, the Q4 elements, as we see that the axis not necessarily parallel to the Cartesian coordinate, the xy, okay? So originally we can put xy, right, previously, okay, with our coordinate, okay? But then if you want, okay, you can also reorientate them, okay, as long as it gives you a proper coordinate system, okay, that represent, if you can see along these directions, okay, this point 4 still match to this point, okay, this point 3 and point 2 still match to this point. So if you look at this particular dimension, it's still a straight line, right? So therefore they not no need to be actually parallel to the original Cartesian coordinate. At the same time, they no need to be 90 degree, okay? usually Cartesian we need 90-degree, right? But for this case we don't have to be 90-degree, right? As long as this axis represent the positions of the node itself in the natural coordinate system. Okay, so this coordinate is still have this point, right? The node 4 and node 3 still have the same t. All right, so this axis is s. Okay, this axis is s, this axis is t. So therefore this, if this is 1, so t equals to 1, and this one t equals to -1, right? So it represents the h. Okay, it doesn't represent the so-called the usual Cartesian coordinate. Okay, it's in the natural form. That's why you may get confused originally. Okay, so you can see that this is the Cartesian coordinate. Okay, but whereas for the other part, okay, this is the natural coordinate. Okay, which they are not parallel, at the same time they can be non-orthogonal. Okay, so how to relate them is still the same. Okay, we have constant plus constant multiplied by s, okay, and also the t, okay, in the x and y directions. Okay, shape functions remain the same. Okay, same form. Okay, 1 minus s, 1 minus t. Okay, previously we have bh, okay, 4bh, right? So we can cancel out. It's actually the similar form. Okay, so that's why it's still the same shape functions. Then for the same shape functions we apply to the displacement function, it still remain unchanged, right? It's still same. Okay, so you will notice that if we compare this isoparametric formulations and this one, the previous few weeks, okay, we derived this for Q4, we will notice that they have similar form, right? But the displacement function not change, right? Only previously we may use uv, now we can use x, y, and so on. Okay, it's just notations that you may want to use to differentiate them. Okay, but if you are familiar, then you can use the same notations. It's not a problem. All right, now again, to derive for the strain displacement and the stress strain relationship, the idea is still the same. Okay, you just have to get the same formulations as the previous. You differentiate respect to the s, okay, the natural frequency, natural coordinate system. Therefore you will get them mapped accordingly to obtain the strain, okay, as well as the stress. Okay, once you get it, you can obtain it accordingly. Right, so this is the idea, right, which you may not need to practice in real using hand, okay, because it may not practical now, okay, to actually use hand. Okay, if you want, you can try to program if you want, right? So here you can see that similar to the previous one, the body force matrix is given as such, okay, as well as the surface force can be given by such. All right, so it will be a 4 times 1 size of the matrix, okay, whereas for this one is 8 times 1 the size of the matrix. All right, because there is there are points, okay, acting on the whole body, right, more than on the surface itself. Okay, 2 times more than the surface itself. Okay, because there are 2 dimensions. All right, so let's check if you have any questions up to now. Okay, you can type in your questions if you have any. If no, then we will proceed. Okay, I don't see any comment yet. Okay, I think there would be a delay in between you type and also in between the life, right? So never mind, okay, you can keep typing, okay, we will address that in the later or Q&A sessions, okay, if we have if you have any questions, okay. But now I will just ask you two questions, okay, just to make you aware. All right, what are the material property required for a three-dimensional structural analysis? Okay, remember previously for a two-dimensional and one-dimensional, we would want the user to insert the area as well as the the Young modulus, right? Okay, so what we need for a three-dimensional structure analysis? Okay, so if you refer to one of the paper, okay, related to a three-dimensional structural analysis for a corrugated core sandwich panel, okay, this is a three-dimensional structure, okay. So what we would put in, if you see there is the Young modulus remain there, okay, but then for a three-dimensional structure you would also need to include a Poisson ratio, okay. Others like density, you may need it to define the body force, right? And also, since there is interactions between this loading nodes, okay, with the corrugated bar, therefore in this paper they include a coefficient of frictions between these two objects, okay. So you will notice that for a three-dimensional structural analysis, not only the Young modulus, you will also need to insert the Poisson ratio, okay, that will give you a proper value of stress or displacement in the later stage, okay. So if you are interested to know why there is E and V, okay, you can refer to a later chapter in any books, okay, for a three-dimensional analysis, and we will notice that in the stress and strain relationship itself, there is a Young modulus as well as Poisson ratio relationship in between here. All right, so that's why, because of this, okay, therefore for a three-dimensional structural analysis, it is critical to also include the Poisson ratio, okay. If we don't, okay, there is a question, if we don't insert density, it doesn't matter. That's right. If you don't insert the density, yes, it doesn't matter if you don't take into the considerations of the weight. All right, if you want to consider the weight, let's say, okay, then you may need to include the density, okay, because of the weight of the body force itself, okay, acting, then that will give you a slight changes, okay, slight difference between when you include real density and without. All right, so another questions that I pose here, okay, is how computer program actually does the integrations. As you can see previously, there is body force, there is surface force, okay, they include integration. So how they actually did all this integration, we can draw in the software with any kind of shape that we want, right? But then that computer program will have to discretize them into the elements, okay. So you may have a smooth surface, but you may represent with different elements, okay, across it, okay, and how the force acting, okay, when we apply, we say we apply a pressure on this area. So how the program actually does these integrations, I believe you have learned this in the numerical methods, okay. So that will lead to what we call numerical integrations, okay. I'm sure you may have learned this, okay. So I just re-highlight, okay. There are two common numerical integrations method that used in the FEA software. Okay, the first one is the Newton Cotes, and the second one is the Gaussian quadrature. Okay, quadrature, right? So in this numerical integrations method itself, okay, we can also see that the Newton Cotes itself, we can divide into whether you want 2 point, 3 point, or 4 point. Okay, so when it is a 2 point, then it is just the trapezoid rules, right? So just recall back, okay, integration is about finding the total area, okay, under the curve. Okay, total area under the curve. Okay, so therefore we can always approximate using what we call numerical integration. We approximate with so-called a trapezium, the simplest one. Okay, then there is a Simpson's 1/3 rules. There are Simpson 3/8 rules, okay, which include different points. So if we intend to use Newton Cotes formulations for our computer program to integrate, then they will use this constant, okay, according to the number of point, okay, for them to do the integration itself. Okay, so if you want to explore more, all right, so basically those commercial FEA software, okay, especially those allows you to do some custom modifications, okay, to their code. Okay, therefore they are very particular, especially for those software that's very high, I would say high, not really high end, but then the idea is that they are more flexible, okay, in terms of accepting changes to their own code. Okay, therefore there is, let's say for Abacus itself, okay, so in Abacus you can always Google, okay, those commercial software, but I don't found any for Lisa FEA so far. Right, what you can see that in the section you can search, for example, for section integrations. Okay, in this kind of software like Abacus, you can actually set which numerical integration method that you want them to apply, okay, by adding a code like section integration equals to Simpson, section integrations equals to Gauss. Okay, so for sure they also have a conditions where they can use it or where they cannot use it. Right, this is where we would say the manual of the FEA software is very important. Okay, any FEA software, their manual is very important. Okay, so for this established, I would say established FEA software like ANSYS, Abacus, okay, and others, Nastran, if you Google, you just Google keywords, okay, maybe you want integrations, okay, with their software name, and you type maybe manual, okay, or documents, okay, then you will find it. Okay, so basically for Abacus you can get the online versions. Okay, some university has subscribed to their online manual. Okay, therefore you can refer. Okay, it's easier for you to search. Okay, I used to search those manual. Okay, it's actually, I think for Abacus itself, the documentations manual will have around 7 volume distinct. Okay, 7 volume, so that's why online version is easier for you to search, right? Then if we want to use the Gaussian quadrature formulas, is actually more accurate, okay, than the Newton Cotes formulations, okay, because it's based on, they call it optimized positions, okay, which is at the midpoint, right? So we can use midpoint to approximate this particular area. Okay, this is using one single sampling point. Okay, so therefore we can obtain the integrations numerically. Okay, but you can see that in numerical methods, in all this numerical integration technique, there is error. Okay, there is error. Okay, you can see there is error here. Okay, so it's up to you to define or your computer capability to handle all these things. Okay, you can always put in the weightage and so on. So this is the table for the Gauss point integrations. All right, so again, when in the FEM software, sometimes when you search or when you read, you will see that they may say the stress is computed at the Gauss point or the integration point. Okay, meaning to say they are using the Gaussian quadrature formulations, okay, which they tells you the locations of their Gauss point. Okay, so if this is the element, so the Gauss point is here, right? If we use the second point or two sampling point Gaussian quadrature, then there will be 2 points, okay, given by this formula, right? This constant. Okay, therefore when they do the integration, they're actually computing at that particular point. So therefore, whatever stress we or whatever displacement, maybe I think mostly it's a stress. Okay, when we get the stress from the software, it's actually computed for every single that particular Gauss point, okay, or the integration point. Okay, not necessarily Gauss. Okay, it can be called integration point, right? So this is the idea behind it. Okay, so for a Q4 type, then there is 4 Gauss point for one particular elements, right? So you can always integrate them after one dimension, then to the second dimension. So you have the 2-dimensional. Okay, similarly for the 3-dimensional cases. Okay, so the evaluations of the stiffness matrix and stress matrix by the Gaussian quadratures method as shown in this generic flow chart. Okay, generally they will do it in this way. Okay, but you can do it on your own, right? This is just a guideline, right? So again, Q&A, if you have any questions so far. Let's see if you have any questions. In normal case, okay, Stanley, you are talking about the density, right? So in normal case, it's preferable if you don't okay, in normal case, normally if we don't take the weight into consideration, yes, you don't have to put in the density. All right, but it's good to put in the density so that it will be used to calculate the weight. Okay, if it is used. Okay, and this density will be very important when we use it for a heat transfer analysis. Okay, for heat transfer analysis, the capability of the heat being transferred throughout a volume, it's very dependent on the mass and the density. So in that case, you may need, right? So it depends on which application you're talking about, which kind of analysis you are dealing with, right? Okay, so okay, so let's get back to this next sections. Okay, we would again ask you some questions for you to realize the importance of it. Okay, so have you ever thought about how large is the stiffness metric in terms of memory? Okay, how large it is? Okay, if you are having 50,000 bar element, let's say, okay, bar element, and how about if we are using not a bar element, we use tetrahedron elements? Okay, the memory will now tremendously increase. Okay, so I just get a quick search. Okay, For a general matrix, okay, numerical matrix itself, you will say that each element that defined in the double precisions, remember when you do a programming, okay, you have to define the type of the memory or the data itself, right? You may define it as an integer, a boolean, a single precisions, double precisions, and so on, okay? So in most of the FEM software, they will treat them as a double precisions, most of them, all right? So if you are taking one double precisions element in the matrix itself, it may require 8 bytes, okay? If you can see, okay, this one is just from SAS company, again a software company that do computational type, not FEA type, okay? But then because the idea of the calculation is still using matrix, so it is similar, all right? So you will see that if the matrix itself contain this number of row and this number of column, it may take 1.8 GB of your memory. In terms of, maybe if we are doing it at that particular moment, then we are talking about the RAM, all right? So if it's about 50,000 bar elements, okay, in that bar elements, you may, when we form the stiffness matrix, it may have 50,001 times 50,001 the size of the matrix. Then therefore it may be around here is about maybe 13 gigabyte, okay, to only storing this stiffness matrix in your RAM, right, before you do the operations, okay? So this is the amount of the memory that you need, okay, if you do not handle it properly. So therefore what we intend to deliver here is that in the FEM software, okay, they would want to compress the storage of this stiffness matrix, okay, in order for us to fit them into the memory, okay, I mean the RAM itself, easier, okay, the amount of size, okay, whenever we access the searching across the RAM is easier and so on, okay? It's more important and it is more computational efficient, right? So how we can achieve this so-called compressed storage of stiffness matrix? We are trying to regroup the stiffness matrix, okay? Because if you still remember, the stiffness matrix may contain a lot of zeros, okay? And they are symmetric, okay? They are symmetric matrix. So therefore, storing 0 for a double, using a double position is still considered double position. They will put 0.000000000, right? So therefore, it will hold memory. Therefore, what we can do, we can compress them, okay, using several methods, okay? We can have the banded symmetric format. We can also use a concept of skyline of stiffness matrix, and another matrix we call it a wavefront methods, okay? So what is banded symmetric matrix? Okay, so in the software itself, when we have this stiffness matrix, there are symmetry, okay, and there are many zeros, okay, in between. But then we will notice that there is, from this particular point, okay, from this symmetry line point, okay, itself, when we calculate, there is a limit or maximum numbers of element that they need, right? So you can see that in this case there will be for a semi part, okay, half of this, the semi band itself is 4, so therefore double of it, because you have the other side, double of it is 8, all right? So how we can calculate this? We can use we can calculate the semi bandwidth of this matrix as given as ND multiplied by M plus 1, okay? So this ND is the degree of freedom, okay, per node. So if you have two-dimensional 2 DOF per node, then this is 2, right? Then you can notice that this now a highlight of this M. This M refer to the maximum difference in the knot number. Alright, so this M is important, okay? In order to have the smaller semi band itself, or the band itself, therefore degree of freedom we cannot control, okay? It's fixed per knot. Therefore we can only control this maximum difference in the knot number, okay? So once we can form this, okay, the rest of the zero is not important, right? So what we do is we will only store this part, okay, in this form. So now it is much more compact, okay, as compared to a large number of zeros, okay? Especially when you have a large number of elements. Just imagine one element, there may only 8 elements in the matrix. For this case are filled up, okay, the rest is zero, okay? You may need a lot of memory to actually store those zero, okay? So what we do is we will see that by having this banded storage itself, we can actually expedite our execution time, the computational time itself, okay? So if we don't use the banded storage method, then the computer may need this amount of time, okay? The unit is just, we don't know, maybe second or a minute. It's just a value that for us to illustrate, okay? Then when the banded storage of K is used, then now we can see that this dimension, the n itself, is now divided in two, okay? The n and this nb, okay, where this nb is our semi band width, right, which we can control now, okay? So the smaller is this, the smaller it is, okay? And this have a power of 2, so whenever we can reduce this nb, the effect is 2 times, right? Is double, okay? So it's power 2, right? So we can see that if we comparing with banded storage and without, then we can save this kind of amount of time, okay, in terms of computation. Therefore, since we are talking about this M, okay, the maximum difference in the knot number, the numbering of the knot is now become important, okay, in order to minimize this NB, okay? If the difference between them is smaller, then the semi-band width will be smaller, right? So what we can do is, in order to reduce the bandwidth, we can do a systematic knot numbering. So in some of the software, again, Lisa FEA, I couldn't search any of these features, okay, but you can found it in other kind of software like Abacus for sure. I've used also as well. There is these features, okay? So what we would see here is that how we can minimize, okay, the M, okay, the maximum difference between the knot number, okay? So imagine these two object, okay, these two objects. So object 1 and object 2, which are constructed using a Q4, okay? So you have a Q4 here, 1, 2, okay? If I number it with 1, 2, 3, 4, then 5, 6, 7, 8. Therefore, in this element, this Q4 element now, okay, you will see that the maximum difference between the knot number will be 5, okay? 6 minus 1, 5, right? This one is only 3, so the maximum is 5, okay? Then we look at the second element, Q4, okay? 7 minus 2 is the highest, so again the difference is 5, okay? So for this kind of arrangement, the M is 5, okay? Now if we number it in this way, okay, a shorter one, we number it along the shorter directions, okay? So you can see this is longer direction, this is shorter dimension. So if we number it 1, 2, 3, 4, 5, 6, 7, 8 in this way, then the M now is 3, okay? 4 minus 1 is 3, 6 minus 3, 3, 8 minus 3, 3, right? So eventually now the NB is reduced from 12 to 8, right, which is 1/3 of it. Okay, so if we can reduce 1/3, then for sure the execute time now is much reduced, right, by 1/3 to the power of 2. Okay, now we have also another way of storing the bandwidth or the matrix, the stiffness matrix itself, by using a skyline. Okay, so skyline concept, we will do it again from the symmetry line. Okay, now we will see like this. Okay, just like a building, we call it skyline, right? So we will look at this. Okay, so there is a maximum number, right, again in this direction. Okay, in the vertical directions we call it skyline. So now we will store it as 1, then x, 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 x0, x, x, and then x, 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 and so on. So we will store in this way. Okay, in the, we will call it skyline way, right? So in generally this will even take lesser storage, okay, than the conventional banded, because now we remove more zeros. Okay, you can see that this 0 is safe, okay, instead of that, right? So this is another method of it. Then there will be another way of solving it. Okay, this one is not really about how we store the stiffness matrix, but this is more on the algorithm itself. Okay, how we going to solve it progressively. Okay, like that's why the name this method take is Wavefront. Okay, from one end to the other. So if you solve it from one element to the other element, okay, progressively, okay, in a Wavefront's way. Okay, so therefore we would say in the Wavefront methods, okay, the assembly of the equations actually alternate, okay, with the Gauss eliminations. Okay, this one, Gauss elimination, is to solve the simultaneous equations. Okay, so this Wavefront method is we will do assembly of the equation, solve it, then progress, assemble again, and solve it, assemble again, solve it. So by doing this progressively, we solve it, then the size of the matrix now becomes smaller and smaller. As we solve more equations, then the size will become smaller and smaller. That's why it forms like a waveform. Okay, so here the numbering now is very important, is the element numbering. Okay, instead of the node. Okay, in this waveform is the element numbering is more important, because when the program do the simultaneous solutions itself, they are doing it by elements, right? They cannot do it by node, right? So therefore when we group them, it will be arranged in the elements, I would say elements, they will solve according to the elements number, right? So therefore the sequence of the operations is important depending on this numbering of elements. So again, let's say we take an examples here. Okay, this one is element 1, element 2, and element 3. Okay, here we use the most efficient, so-called most efficient number, not numbering. Okay, it doesn't matter actually. So this, when we try to assemble our equations, okay, so we will see that when we assemble for element number 1, okay, we will see that since element number 1, this part may be constrained, right, to a boundary conditions. Therefore when we try to solve for this 4 equation, okay, at node 1, 2, 3, 4, okay, then node 1 and 2 can be solved because of our boundary conditions given. All right, therefore node 1 and 2 can be eliminated from the assemble of the equation itself, okay, leaving only 3 and 4. Okay, So leaving only 3 and 4 and bring it to the second one. Okay, so for the second one, then there's 3, 4, 5, 6, and when we try to solve it, since this is connected, okay, and they are related to each other, no other external boundary conditions, then we can solve for 3 and 4, right? We can eliminate 3 and 4, leaving 5 and 6. Okay, then 5 and 6 remain here, right? Then we solve it accordingly. So you can see that the size of the assemble of the equations actually being limited to maybe 4 nodes in this case, right? So that is how we can save or simplify the solution. Instead of loading the whole matrix, we will solve it according to this. Okay, we call it a wavefront methods. Okay, so now if we use not efficient, let's say not efficient way of numbering the elements. Okay, we jump from 1, 2 and 3 at the middle. Then what happens is that same concept. Okay, solve for the first element. Okay, we can solve for not 1 and 2, okay, leaving only 3 and 4. So 3 and 4 will bring to our second element, which is here. Okay, second element have 5, 6, 7, 8, okay, plus the 3, 4 previously, and they cannot be solved. Okay, only 7 and 8 may be able to be solved because of the boundary over here. Then leaving only leaving 3, 4, 5, 6, okay, for this next part. Okay, then you can see that this assemble of the equations now consists of 6 nodes, okay, instead of previously 4. Okay, that's why the numbering of the elements now become important in this so-called wavefront methods. Okay, so this wavefront methods is computationally more efficient than the banded matrix because it doesn't load the whole thing. Okay, it solve it part by part, right? And in the wavefront, this block of zeros coefficients are not stored or processed. Okay, so since you don't have to load the whole matrix, then therefore no zeros that you have to deal with most of the time. Okay, so here just one question for tutorial that you can practice. Okay, and that's all for these sessions. All right, so any questions? Okay, quick one. All right, so you can okay, I guess I will put the link in the comment box before I forgot, right? So you can log in using this link, and I will put this link also in the Google Classroom. Let's see. Okay, then also you can also take a quiz. Now I think it's already available in the Google Classroom. Okay, the quiz number 3, okay, to test your understanding on these sections. Okay, so you can try it immediately. Okay, if you don't, since it's still fresh with you. Okay, so you don't have to take more time to actually do the revision and so on. All right, so make sure you log in using your student email. All right, and this is the Google form link for this quiz. Okay, this link again, you can get it in the Google Classroom, right? So make sure every one of you okay, if you can't scan, you just use the link, okay, that I provide. So you just click it, and then you make sure you log in using your student ID. All right, same thing for the Google Classroom. Make sure every one of you now try to log in, because I need to prepare you for the tests, okay, which will replace the final exam. Right now you don't have the final exam, so that test will be more important. So you have to go in, make sure everyone can log in. When everyone can log in and no problem, then I will therefore start the design of the test, and we will do it at the same time. All right, so any more questions? if you don't have any questions, okay, maybe I just share quickly on the e-portfolio. All right, I already post that in the Google Classroom as well. All right, but then I may want to just quickly highlight to you, okay, the whole ideas, right, in a more detailed way. All right. Okay. Now, can you see? Yeah. Okay. So here is the document that I have put there, right? So you can see that they are available everywhere, all right, actually. And you have the idea of this e-portfolio actually is just a collection of those work that you have put in, all right? So you don't have to really put in a lot of too much effort on designing the whole website, right? But then you just design as long as it's easy to browse, okay? When I look at it, it's easy to browse. So just like when you browse a website, okay, you want something easy to find, okay? The flow of the website will be very important, okay, to ease the user or the reader to browse through your website, okay? So you can check out other e-portfolio, okay? You may, all right, okay, they may be good, maybe not good, okay, but make sure you don't do it in the very last minute, okay? Just start putting whatever you have done in that website, okay, of your e-portfolio, all right? Just progressively, some work, okay, you can put it just like a blog itself, okay, to store your work, right? So that it shows a flow of your work, okay, your ability to do that particular work, right? So make sure you don't do it, and because of this is related to website, you are actually not able to copy directly, right? So make sure you read through properly before you post it on the website, right? So you can always use your student email to log in, okay? Actually, why I want you to use the student ID to log in on all this Google ecosystem is because you have a large number of storage, okay? You don't have the problem of maybe your email is full, okay, your Google Drive is full, and so on, okay? Just log in using the student ID, okay? Your student ID, I think you may have like 5 terabyte of storage, if I recall properly, all right? Long time back, I recall this 5 tera, I guess, okay? I might be bigger than my actual hard drive actually. So what you can do is you just host, okay, click, and then you can start doing this, okay? So this is very intuitive, okay? You just drag and drop, okay, and so on, okay? So it's easy for you to learn actually. So the suggestions of the content that you may want to put in is you have to describe your task, okay? Then what you want to do in the task, okay, how you deal with it, okay? This is the methodology where you may put in some theory, why you select the elements, and so on, all right? Then what are the results, and you discuss about it. Then you may do some reflective comment, like your personal view, like whether this is correct, this is not correct, okay, what can be improved, okay, what is difficult when doing this assignment from your perspective without computer, or maybe the software is not good, or whatever it is, right? The reflective type of comment, what you actually learn, okay, by doing this task, right? Then these are the rubrics, okay, we may not go through this, okay, and now I will go through the tasks, okay. Basically there are only 3 tasks that you may need to complete, right? We have shown this to you previously, I just regroup them, all right? And also this one, okay, you just take a simple video, okay, and put it in your website, okay, in your e-portfolio website, right? Then the last part will be this. Okay, what you need to do is you have to select one heat transfer problem. Okay, one heat transfer problem. Okay, so this figures only an example for you. Okay, I just get this from internet or maybe a book. I forgot. All right, you just get some idea maybe from papers or whatever it is. Okay, so from that heat transfer problem, now you define it or you try to solve it on your own. Okay, using your own method. Okay, simulate the heat transfer problem to obtain the temperature profile, how the temperature actually change. Okay, so if whatever not defined, you define it yourself. All right, so make sure all the definitions of maybe material property or whatever it is rational. Okay, is reasonable. Okay, is based on some fact. Okay, or maybe reference. Okay, so for example, I think this this one is taken from this website. Okay, it's related to the thin film deposition process. Okay, and then this one is about the passive heat exchanger from the LISA FEA. Right, so you may use different kind of heat transfer problem, any problem. Okay, it can be from the book as well. Okay, just take one problem from the back and you do it your way. All right, okay, I think that's all. I hope that's clear. Let's check again. Share the codes again. The link also same last time. I informed them, but they have not fixed it. Okay, so never mind about the attendance link. I will share it in the Google Classroom. Just log into the Google Classroom and you can click it there. All right, so if you still have other questions, feel free to message me in the Google Classroom or whatever it is. All right, so I hope that's all. Okay, it's clear for you, and that's it for this week. Okay, so happy trying the quiz. Make sure you try it before you forgot everything and more assignment coming in. Right, so try as early as possible. Right, so see you. Bye bye.